Okay, thanks very much. I'm going to talk about some work that I did, two pieces of work with Yoav Freund and Samori Patufe. And this was work that was, to a large degree inspired by specific results of Partha's. So the theme of the work is manifold learning. And so basically about 15 years ago, people in the machine learning community started getting really excited about this whole topic of manifold learning. Yeah, the idea was just that a lot of the data that had seemed extremely high dimensional, might actually be tractable just because it happens to lie on a low dimensional manifold. And let me give you some examples. So for instance, suppose you were trying to come up with models for animation. One thing you could do is to find a particular subject and put a lot of markers on their body, make them walk around, and then measure the positions of these markers as they were walking. So for instance, let's say you put 100 markers, okay, on a person's body. As the person's walking, each marker is a three-dimensional position. And so you get 300 numbers. There's 300-dimensional time series. But these 300 numbers are not independent of each other because essentially they're functions of just a few joint angles in the body. So maybe the real number of degrees of freedom is just something like 10 or 20. And so the data is actually, say, a 20-dimensional manifold in 300-dimensional space. And so, the hope was to exploit something like this. Let me give you another example. I'll give you an example of these speech signals because this is an example that I think Partha used a lot. There was this one talk that I think he gave many, many times, year after year. I think you know the one I'm talking about. It was, I personally saw it about 4 or 5 times. And he asked me once, he said, Sanjoy, are you getting bored of this by now? And I remember just thinking that, I used to just love hearing this talk. It was, because it was so fundamental. It was like, one of the Star Wars movies or something like that, You just like watching it again and again because it's so good. And so, so he had this example there of speech signals where, so speech is just this one-dimensional time series, but the way people deal with it is that they look at a window of the signal, and then they apply lots of filters within the window. And, the more filters you apply, you can get an arbitrarily high-dimensional representation. But the bottom line is that this speech is produced by a physical apparatus with just a few degrees of freedom. And so once again, this sort of manifold hypothesis comes into play. And so, so these sort of realizations that there were these systems with very specific physical or geometric constraints that generate a manifold led to this great excitement in machine learning and this area of manifold learning. And there was a time, I think roughly around 2000, when just a huge number of manifold learning schemes were coming out. And with a lot of them, it was not clear exactly what problem they were solving, what kind of manifold they were dealing with, whether any formal claims could be made. But there was a lot of excitement around all of this, and it was clear that they were really trying to get at something fundamental. So then Partha sort of decided to get in on the action, and he had a bunch of papers that really brought a lot of rigor to the field. And I'm sure many of you are familiar with a lot of them. I'm going to briefly mention one of them, which was joint work with Steve Smale and Shmuel Weinberger. And this was a really nice paper. I mean, so this manifold hypothesis that things lie on a manifold, so if you suppose data lies on a one-dimensional manifold, it's not that helpful if that manifold happens to be a space-filling curve. Okay, so in order for this manifold hypothesis to be helpful, you have to, it has to be the case that the manifold is not curving too much, or it does not fold back on itself too much. But those of us like me who were really quite ignorant of differential geometry didn't know how to formalize these conditions at all. And one of the nice things about this paper was that Partha and Steve and Shmuel Weinberger came up with a very nice condition on a manifold, something that would make it very well behaved. And they called this the condition number. It was a sort of a curvature condition. And they said that, you have the manifold and you grow normals, and you look at the first point at which these normals intersect. So, for instance, if you have a sphere, the first point at which they're going to intersect is at the center, so it's the radius. And so the bigger the radius, the better the situation. Okay? And so that was the condition number. And in addition to this definition, they had a bunch of properties of these kinds of nice manifolds. And this was just a godsend for a lot of people, a lot of theoreticians who wanted to work on this field, but whose background was mostly in algorithmics, because it made it possible to work on manifold learning without knowing any differential geometry whatsoever. These properties provided the interface to manifold. And after this paper, there were really quite a lot of very interesting results on manifold learning. So let me tell you about one of them, which is this was by Baraniuk-Wakin and by Ken Clarkson. And so this was a really nice sort of follow-up to the famous Johnson-Lindenstrauss lemma. So the Johnson-Lindenstrauss lemma says that if you have n points in Euclidean space, arbitrarily high dimension, you can project them. You can choose a random subspace of dimension order log n, and distances between points will be approximately preserved. Very powerful theorem. But it applies to finite point sets, n points. What happens if you have infinitely many points, but they happen to lie on a manifold, one of these nice manifolds with a finite condition number? So what these people showed is that once again, a Johnson-Lindenstrauss type effect occurs. And so the manifold, let's say it's little d dimensional, and it's in some super high dimensional space, it doesn't matter. You can project it to just order d dimensions. You can choose a random subspace of dimension just order d, and all infinitely many interpoint distances will be preserved approximately. Okay, so this is a very powerful Johnson-Lindenstrauss type effect. And this was made possible essentially by, by this definition. It sort of pointed the way to a nice class of manifolds about which one could prove all sorts of results. Okay. Now, also inspired by Partha's work, I started working with Yoav Freund, and we were interested in non-parametrics. And the reason for that is that, well, the cursive dimension, has many shapes and forms in statistics. It arises in many different statistical estimation problems, but it's in non-parametrics that the curse is really most keenly felt, okay? And that's because the convergence rates are exponential in the dimension. So by non-parametrics, I mean things like histograms, density estimation, regression, and so on. And in general, if you have n data points, and you're in some large dimension D, the error rate of estimators looks something like this. The constants are all wrong. Maybe there's a 2 or a 4 or something like that. But what that means is that if you want to half the error of the estimator, you need 2 to the d times as much data. And so if d is something like 100, this is just out of the question. And it makes it seem that basically there is no point in doing non-parametrics in this sort of high-dimensional space. But the question then arises, what if the data has low intrinsic dimension? What if the data is in 1,000 dimensions, but it lies on a 3-dimensional manifold? What is the relevant parameter, the 1,000 or the 3? Now, we wanted to look at it in slightly more generality, because at the same time that, this sort of manifold dimension this concept of manifold dimension was going around, there were also other types of low intrinsic dimension that was circulating. One example is sparsity. So you have a text data set where, what you do is you choose your 50,000 favorite words, and each document is represented as a 50,000 dimensional vector, where for each word you say whether or not it occurs in the document. So it's absurdly high dimensional, but if the document has only, say, 100 words in it, there are only 100 non-zero values. So it's also a type of intrinsic low dimensionality, but it's not one of the kind of nice manifolds that, that came up earlier. And so in that situation, again, the question arises, what is the real dimension over here? Is it 50,000 or is it 100? What is the dimension that controls the rate of convergence of these non-parametric estimators? And so what we wanted was some sort of umbrella notion of dimension that would have these as special cases, the manifold dimension, the sparsity dimension, and so on. And we actually worked with a few notions, but one of them was this notion of a doubling dimension, okay? And so if you have a set in some high dimensional space, it doesn't matter what, we'll just say that it has doubling dimension little d if if you look at any ball in space, and you look at the part of the set that lies in that ball, it can be covered by 2 to the d balls of half the radius. Okay? So, for instance, let's say you have a line in some high-dimensional space. Okay? Pick any ball. You can cover it by 2 balls of half the radius. Okay, so look at the line, look at any ball. That's the part that lies in the ball. You can cover it by 2 balls of half the radius. So we say the doubling dimension in that case is 1. If the set happens to be a flat, a k flat, then the doubling dimension is order k. If you have endpoints, if you have a finite set of endpoints, well, you can always cover endpoints by n balls. And so the doubling dimension is at most log n. Now, for the manifold case, once you have the condition number, well, locally, then it looks very much like a flat. And so in small enough neighborhoods, the doubling dimension is order k. And if you have one of these sparse data sets, so k sparse, let's say you're in big D dimensions, but each data point has only k non-zero coordinates, well, then you lie in a union of k flats. You know, D choose k flats. And so the doubling dimension is at most k log D. So it's kind of nice. You know, it's this nice notion of dimension that includes some of these other things as special cases. And so, you know, we wanted to work with this. And so the goal was that we wanted to come up with non-parametric estimators for the standard tasks, vector quantization, which k means regression classification. And in these estimators, the usual dimension is the big D, the big dimension that the points lie in. We wanted to basically cross that out and put in like the little doubling dimension. That was kind of the goal, and it's something that we did manage to achieve using using a new spatial data structure actually, and so let me just say a little bit about that. Okay, so a very common way to do non-parametrics is by spatial partitioning. So you take space and then you carve it up into a whole bunch of cells. Okay, so you have some space, however high dimensional, you divide it into cells, and then within each cell you have a really simple model, like just a constant. Okay, so let's say within each cell you just have, let's say you're doing regression, you simply have the average y value within each cell. Okay, now in estimators like this, the trade-off is always between the number of cells and the diameter of the cells. So ideally, you want these cells to be really small, because if they're small, then it's unlikely that the y value is going to vary a lot within the cell. So in order to reduce bias, you want the cells to have small diameter. But at the same time, you don't want to have too many cells, because you're splitting your data points between the cells. So if you have too many cells, there are very few points within each cell. And so you will not be able to estimate the y value within the cell very accurately. That's the variance. And so there's this standard trade-off. And so our starting point to working on this was actually just to try and clarify what is meant by the diameter of a cell. Okay. It turns out that most of the work in non-parametrics, when they talk about the diameter of a cell, say this is one cell right here, they're literally talking about the physical diameter of the cell. You know, that thing. But the other diameter you could talk about is sort of the effective diameter, say the average or the maximum interpoint distance within a cell. And the one we really would like to use is the average expected interpoint distance within a cell. Now, the nice thing about that, so the bad thing about working with this physical diameter is that, you know, if you're doing the analysis, the only way you can analyze the physical diameter is really if the cells are very regularly shaped, like they're all nice boxes. If you have weird shaped cells, it's very hard to get a handle on what the physical diameter is. But if you're working with the data diameter, it doesn't matter how freaky the cells look. All you care about is the expected interpoint distance within the cells. And so by moving to this notion of diameter, it really kind of makes it possible to have, to have sort of more, slightly less orthodox partitioning schemes. Okay, and it turned out that actually, although most of the work uses physical diameter, if you put the effective diameter in there as well, you can get the same sort of results for these convergence rates of nonparametrics. Okay, so with that in mind, we then, so we said, okay, so we want to look at spatial partitioning schemes. So the first question was, well, you know, maybe some of the existing schemes are already adaptive to intrinsic dimension. Who knows? Let's check. And so we looked at what is possibly the most popular space partitioning scheme. This is the KD tree. And in case you're not familiar with this, the way it works is you have a bunch of points and you put a box around it. And then you pick one coordinate direction and you split it the median on that direction. And then you recurse on the two halves. Okay, so you pick the median, you pick another direction, split it the median, and so on. And in this way, you get a whole bunch of boxes. So you essentially get a tree structure where the number of cells doubles at each level. And then when you get a query, you just move it down the tree. And if it's regression, then you just return the average Y value within the cell. If it's nearest neighbor, you return the nearest neighbor in the cell, which is not its real nearest neighbor, and so on. Okay? And once again, the same considerations apply. You don't want to have too many cells, and you want the diameter of the cells to be small. So the real question is, as we move down the tree, how fast does the diameter shrink? Because we know at each level you're doubling the number of cells. So the only mystery is, how fast does the diameter shrink? And this is what we wanted to investigate for KD trees. At what rate does diameter decrease as you move down the tree? And it turns out that it decreases painfully slowly. Okay, and so let me, so let me just give you an example. So you consider a data set that is really sparse, okay? Exceptionally low intrinsic dimension. It's so sparse that each point has only, you're in D dimensions, but each point has only one non-zero coordinate. Okay, so some points lie along the x1 axis between -1 and +1. Some points lie along the x2 axis between -1 and +1, and so on. So the data basically looks like a union of these line segments. Okay, super sparse data set. So let's look at what happens to the diameter as you move down the tree. So initially, the diameter is 2. Now you pick a coordinate direction and you split it the median. Let's say you pick this and you split it the median. The diameter is still 2. You pick another direction and you split it the median. The diameter is still 2, and so on. And in order to get the diameter down to 1, you need to do big D splits. Okay, so if you're in 1,000 dimensions, you need to do 1,000 levels of the KD tree just to get the diameter down from 2 to 1. That's terrible. You know, in order to do that, you need 2 to the 1,000 points at least. So that's really bad news. And yet, this is a data set where by any sensible measure of dimension, this has incredibly low intrinsic dimension. The doubling dimension is log big D. Okay, and although under other notions of dimension, you would say it's just one-dimensional. Okay, so something with low intrinsic dimension, and so the KD tree wasn't doing the job basically, and so we figured that we had to do something else, had to come up with a different partitioning scheme, but we just had to tweak it a little bit. So here's what we did. So you just need to make 2 little tweaks. Instead of splitting along coordinate axes, pick a random direction. So pick a direction at random from the unit sphere. And instead of splitting exactly at the median, take the median and add a little noise to it. Okay? And so you get some, so maybe initially you pick this direction, you have the median, you add a little noise to it, and then you recurse on the 2 halves. So you get something that looks like this. As we call this a random projection tree. Okay? And it turns out that if you do that, then you half the diameter in just little d levels instead of big D. Okay, so this is the only tweak you need to make. Okay, and so we call these random projection trees, and I'll tell you a little about them in a second. Oh, yeah, Vin.
Doubling dimension.
Right. Okay. So we showed this for actually a couple of different notions of dimension. For doubling dimension, we needed little d log little d, and I'll put up that result right now. Okay. So yeah, we also came up with our own notions of dimension, but here's the result for doubling dimension. Okay, so this was the definition again of doubling dimension. If you cover a ball with 2 to the d balls of half the radius, and so here's the theorem over here. You build one of these trees using a data set. Now, look at any cell in the tree. Let's say the points in the cell happen to have a doubling dimension little d. then if you go d log d levels down further in the tree, every cell down there will have half the diameter of the starting cell. Okay? So basically, you half the diameter every little d log little d levels. And so it was a much better rate than is achieved by KD trees. Okay, so how much time do I have, by the way? Because maybe I'll say a little bit about the proof. 10 minutes? Okay, so let me just say a little bit about why this works. So if coordinate projections are so bad, how can a random projection work? And basically, the answer is that it's not that coordinate projections are bad. It's just on some data sets, coordinate projections work fantastically well. On other data sets, coordinate projections work poorly. Random projections never work fantastically well, but nor are they ever bad. They're always pretty good. They're reliably pretty good. Okay, that no matter what the data set, that's kind of that's kind of what comes out in the analysis. They're very predictable. Okay, and so let's look at some examples of this type of predictability. So here's one question. You have a line segment. You project onto you project onto some direction. What happens to the length of the line segment? If you're doing a coordinate projection, it really depends. It could be that if you're projecting onto this coordinate, it shrinks to 0. If very bad. If you're projecting onto this coordinate, it remains 1. Very good. In a random projection, things are much more predictable. Basically, its length is going to shrink to 1 over square root d, and there are nice tail bounds for what the deviation is going to be. Okay? Things work in a much more predictable manner. So that's what happens to the lengths of vectors. Now, the next relevant question is, what happens to the diameter of a set? So, so what's happening in these random projection trees is you always pick a random line, you project everything onto the line, and you split it in the median. So when you have a set of a certain diameter and you project onto a line, what happens to the diameter of the set? Okay. Now, if you have a full dimensional set and you project onto a line, obviously the diameter remains the same. Okay. And but now, what if your set happens to have low doubling dimension? So you have a set that lies in this ball. So this is the diameter of the set. But it has low doubling dimension. If it has low doubling dimension, it means that it cannot possibly fill up this ball. It's occupying just a very small amount of space in the ball. And so you would actually expect the diameter to shrink considerably once you project it onto a line. So the points look something like that. They occupy just a small portion of the ball. The doubling condition guarantees you that you have very small covers for the points on this ball. And so you can show, I won't go through the analysis, but basically you can show that very predictably, the diameter shrinks by a factor of square root little d over big D. Okay? And just it behaves in a very regular way. So now let me explain why this particular random tree construction works. Okay, so you're building this tree. At a certain point, you have a bunch of points, and let's say currently the radius of the points is 1. So all the points happen to lie in this ball. You want to show that once you build the tree, another d log d levels down, everything will have radius at most a half. Okay, so how do you do that? Well, first of all, because the points have low doubling dimension, it means they have small covers. Okay, so let's pick a cover of radius epsilon equals 1 over square root little d. You don't need too many balls of that radius in order to cover the points. The number of balls of that radius that you need depends only on the intrinsic dimension. Okay, so you need just a few balls, and so all the points lie inside one of these balls. Now, pick any two balls that are far away, like these two. You can show that any one of these splitting steps, where you project onto a direction and split it in the median, has got a constant probability of cleanly splitting these two. So something like that. Literally, this goes on that side, that goes on the other side. So with constant probability, for any two balls, you're going to cleanly split them. And there aren't all that many balls. So after d log d levels, you're going to cleanly split everything. And so d log d levels down, any pair of balls that is far away will have been cleanly split. And so the only balls that are left together in the same cell are those that are close together. And therefore, the radius, instead of being 1, is now only a half. The diameter is a half, okay? And so, so I just have to explain why this is true. Why is it the case that when you have two balls like this that are far away and you project onto a random direction and do the median, why is there a constant probability of splitting them? And that boils down to these sort of regularity or predictability properties of random projection. Okay, so you have an overall ball of radius 1, and you have these two balls inside it that are pretty small, and that are quite a lot of distance apart, say distance a half apart. What happens when you project onto a random line? Let's say you project onto a random line. Well, the two balls are far apart, so we know random projection shrinks distances by a predictable amount. So the distance between the projections is going to be about 1 over square root big D, predictably. We know random projection does predictable things to diameter. So if it's initially 1 over square root little d, when you project it, it's going to be 1 over square root big D. Everything's as expected, you know. And then, so you have, if each thing projects to something of 1 over square root big D, the distance between them is 1 over square root big D, you can argue that the median is going to also be in somewhere here. Adding noise makes it rather like sampling uniformly at random from here, and so you have a constant probability of actually cleanly splitting them. And so you get this, and so you get this nice behavior. Okay, so it's all based on these predictability of random projection. So to return to non-parametrics, what this implies then is that, so when we were talking about diameter for the RP tree, we were really talking about this data diameter, the interpoint distance. And so what this implies for regression, and this was work done mostly by Samori Patufe, was that suppose you're doing non-parametric regression. You have a bunch of points. You want to find a function to minimize the squared error. And so what is the smoothness assumption on the target? Well, let's say it's Lipschitz. Well, then we know from Stone that this is really the best rate you can hope for in general if the dimension is big D. And this is the cursive dimension over here. But for doubling dimension little d, you can basically now replace this big D with D log D. Okay, and that just follows from using RP trees, and then you have to make some more arguments, basically to the effect that this average distance is really, is a kosher substitute for the physical diameter that used to appear in the standard.
Are you assuming that the data lies down low dimension?
That it has doubling dimension little d, yeah. Yeah, absolutely not, yeah. Yeah, so and this is for these spatial data structures. So, so what are some open questions? Well, so we can get the exponent. If the data has doubling dimension d, we can get the exponent in those non-parametric bounds down from big D to little d log little d. But how about just d? So that's something that is. Peter Bickel and Lee have a way to do non-parametric regression. Using kernels for which they're able to achieve this. And the question is, can you do it sort of more generally? Is there sort of a generic way to do this? Random projections, what about other splitting rules that are not necessarily quite as quick and dirty, like using the covariance matrix to decide the direction of a split? Now that there are actually some nice formalizations of low intrinsic dimension, it would be really nice to get a sense experimentally of how widespread it is. And I haven't seen any really compelling experiments with real error bars on the kind of dimensions that people obtain to argue that this is a widespread phenomenon. And finally, there are really a lot of heuristics for manifold learning that are yet to be analyzed. And it would be very interesting to analyze some of them under this assumption. So, I mean, I actually do not work that much on manifold learning anymore, and I think that probably some of the some of the hype about it in the machine learning community has subsided somewhat. a lot of very interesting questions were identified. Some of the easier problems were solved, and a lot of very important questions remain. But yeah, I think but during the heyday, there was really a lot of fun and excitement, around the topic, and a lot of it were due to Partha, and so I wanted to talk about this. Okay, thanks.